All right. Good afternoon, everyone, and welcome to today's GSSA Lunchtime lecture. Before we begin, I'd like to thank our sponsors for these talks for the month of July, TerraCore Geospectral Imaging. Thank you guys for your continued support. So I have the pleasure today of introducing Tebogo Makhubela. Tebogo is a lecturer in the Department of Geology at the University of Johannesburg. He started his BSc in Geology and Geochemistry and Chemistry at UJ in 2009, and continued to complete his honors, MSc, and PhD in Geology by 2019. He became a full staff member at UJ when he got appointed assistant lecturer in 2015, and was then appointed into a lecturer position in the New Generation of Academics program, or NGAP, in 2016. Tebogo's research specializes in cosmogenic nuclide methods, uranium, thorium, helium dating, and argon-argon dating in quaternary environments and the Earth's surface. Tebogo's research has been mainly in the caves of the Cradle of Humankind, UNESCO World Heritage Site, but he is also interested in the application of Earth surface geochemistry in different geologic settings of Southern Africa. He is here today to tell us about the role of cosmogenic nuclides in determining recent surface changes and processes in South Africa. Welcome to Tebogo. Thank you for joining us, and over to you.
Thank you, Natalie. Okay, thank you all for coming to listen to this talk. So I thought I should take advantage of the platform and introduce cosmogenic nuclides to those who are not familiar with them and their role in helping us understand the landscape evolution of Southern Africa. So this title that I have is slightly different from the original title. However, it speaks to the same topic. Okay, right. So in this talk, I am going to start by briefly talking about the production, uses, and types of these so-called cosmogenic nuclides. I feel that an introduction is very important because this is not something we cover in the curriculum in South Africa, and I don't think many people are familiar with them. Then I will move on to talk about the sample processing and measurements of cosmogenic nuclides, especially from a South African perspective. Then I will briefly talk about the landscape evolution of Southern Africa before moving on to the cosmogenic data in Southern Africa. And for that, I'm also going to use some specific examples of studies that have been carried out in Southern Africa. So these so-called cosmogenic nuclides, they are rare isotopes that are formed when primary galactic cosmic rays that are entering our atmosphere collide with atmospheric gases and produce a cascade of secondary electrons, which are high energy neutrons. And these go on to produce cosmogenic nuclides in the atmosphere, which are called meteoric cosmogenic nuclides. And then the high energy neutrons that made it all the way to the surface of the Earth, they then produce cosmogenic nuclides in the, sorry about that. They then produce cosmogenic nuclides in the minerals, in the rocks on surface, and those are called in situ beryllium, rather in situ cosmogenic nuclides. So applications of cosmogenic nuclides, they're very diverse. The nuclides that have been accumulated in the rocks and sediments on surface can be used to determine the age. For example, an exposure age, which gives an idea of how long a surface or a material has been sitting on the surface, exposed to the cosmic rays as they come and they produce these nuclides on the rock or the surface. As well as burial dating, which works in the way that something that was previously exposed on surface is now buried at some depth where the production of cosmogenic nuclides is now taking place. And as a result, the radioactive cosmogenic nuclides, they start decaying. And by looking at the decay rate of those nuclides, we can determine the age of how long something was buried. And the radioactive cosmogenic nuclides can be paired with the stable cosmogenic nuclides, such as helium-3 or neon-21. And these can also be used for burial age dating. However, we can also use the nuclides accumulated on surfaces, rocks, minerals on surface to determine the denudation rate. This is the erosion rate, or the sedimentation rate, or the fall slip rate, and there are many other plenty applications. In this talk, as you will notice, I'm going to focus mainly on the denudation rate because I want to focus on the landscape evolution of Southern Africa from a cosmogenic nuclide perspective. In this table, well, these are the most common cosmogenic nuclides that are used in earth science applications. However, in this list of the most common, beryllium-10 and aluminium-26 are the most common that are used in about 80% of the studies that are produced. And these are carried out in quads, and they are mostly produced by spallation reactions. Simply indicated here, for example, we have a high energy neutron impacting an oxygen atom in quads, in whatever rock, it could be a sandstone or a granite. And then we have beryllium-10 being produced together with 3 neutrons and 4 protons. And these neutrons and protons do not actually continue the cascade of cosmogenic production. It is only the high energy protons that are formed in the atmosphere. And that's how it is for, well, aluminium-26 using silicon in quads. So in quads, beryllium-10 and aluminium-26, they are produced at a known rate of about 5.5 atoms per gram per year. That is how rare it is, how rare they are, because imagine about 5 atoms per gram and produced in a year of beryllium, and it is about 35 atoms per gram per year for aluminium-26. And this gives us a ratio of about 1.6, but it is commonly assumed to be 1.6, 1 is to 6.75. And the production of these isotopes, they have known relationships to the altitude, the latitude of where you are on Earth, as well as the depth at which you are sampling. And because of the half-lives of 1.39 for a million years for beryllium-10 and 700,000 for aluminium-26, we are able to do a burial dating up to about 5.3 million years. So all the way to about the Pliocene. Okay, so now I want to talk a bit about the sample processing and measurements of cosmogenic nuclides from a South African perspective. But generally, sample preparation and processing for cosmogenic nuclides starts similarly to other geologic processes, whereby you want to crush, knead, and sieve your rock or sediments, and then you want a fraction. Commonly, that's about 0.2 to 0.8 millimeters. And thereafter, you want to separate your quartz from all the minerals that are in your rock or your sediment. And you can start by using a magnet to separate magnetics, and then you can move on to use HCl to separate the carbonates. And thereafter, you can use heavy liquid density separation to remove the heavy minerals, such as zircons. And then you can also do froth flotation to remove the feldspars as well as the micas. And ultimately, you want to use concentrated, or actually a mixture of dilute hydrofluoric and nitric acid. And this will be multiple times, commonly about 3 times for a duration of about 24 to 72 hours. And here you are then etching the grains of the quartz grains, and you're removing the meteoric beryllium-10 as well as other cosmogenic nuclides that are stuck on the surfaces of the grains, because we're looking for the in-situ produced cosmogenic nuclides. Once we have pure quartz, then we can proceed to, do complete the dissolution of that quartz and then run columns to separate beryllium-10 from aluminium-26. And from that point, we can then dry down and prepare the targets for AMS measurements. And these are in the oxide phase of the 2 metals, beryllium and aluminium. So in South Africa, if you want to process cosmogenic nuclides as we speak, there is only one place where you can do this, and this is at the Wits Isotope Geochemistry Laboratory, which is commonly known as the WIGL. And there we have set up methods for processing beryllium-10 as well as aluminum-26. And this was done during the MSc project of Sibusiso Konyana, this gentleman over here, whom I co-supervised with Stefan Winkler from the Itemba Labs, and Jan Krommers was actually the supervisor. Itemba Labs, well, that is the only place where the only accelerator spectrometer in the continent is housed at the Itemba Labs facility here in Gauteng. And AMS is actually the only preferred technique for measuring the cosmogenic nuclides. And it is a gigantic instrument. Maybe some of you are able to see from the photos, but just to give you an idea of how gigantic it is, I think that is about 15 to 20 meters long, and that should be closer to about 10, if not more, 10 meters long. That's how gigantic this system is. And this is based on the 6 megavolt tandem accelerator, which was recently well improved at the NRF Itemba Labs. And we use this to then measure the cosmogenic nuclides. Now let's move on to, well, the main reason for this talk, which is the landscape evolution of Southern Africa and how the cosmogenic nuclides have been used to understand what has happened since the Pliocene in Southern Africa. The starting point, if we want to discuss the nature, origin, as well as the erosion history of Southern African landscape is, well, the model for the geomorphic evolution of Southern Africa, presented by Partridge and Maud, as well as Partridge in 1998. So this model is based on about 83 years of studies on the Southern African landscape, and they were aiming to actually, well, resolve the controversies on this topic in all these studies. And they used field measurements and correlation of erosion surfaces and the data kimberlites to come up with a model that suggested, well, it sort of improved on earlier studies by Lester King and said, indeed, the backwearing of the Great Escarpment that was formed since the breakup of Gondwana was retreating at about 1,000 meters per million years during that, well, since the Cretaceous period, due to the tropical to humid climate. And coeval with that was actually the downwelling erosion of the interior plateau of about 200 meters per million years. And these two processes, the periplanation of the escarpment as well as the periplanation of the surface above the escarpment and below the escarpment, resulted in the formation of the African surface. And this was at the end of the Cretaceous period. And later on, around the Miocene, they suggest that there was a minor uplift of about 150 to 300 meters, forming the post-African surface the post-African one surface. And a little later after that, in the Pliocene, they suggested a renewed, rapid asymmetric uplift, whereby the eastern margin of Southern Africa was uplifted by about 1,150 meters, whereas to the west it was a slightly less uplift of about 300 meters. And this uplift resulted in the formation of the post-African two surface. So this model is generally accepted, and it makes a lot of sense. In fact, it is what most of us teach at university. However, And there are some controversies regarding the uplift and the denudation rate of this model, particularly in the Cenozoic period or era. An example is studies by Brown et al. As well as Van der Beek et al., who used appetite fission track thermochronology to argue that the Drakensberg escarpment is actually an inherited escarpment since the breakup of Gondwana in the Cretaceous, and that well, the retreat has been limited to less than 30 kilometers with a denudation rate for the downwelling rates of up to 200 meters without any uplift in the Cenozoic. Other studies have actually supported these using depth profiles of kimberlite diatrines in the sediment and lava xenoliths in them. And interestingly, well, in the Patrician Mott paper, they do suggest similar values to the studies of Hansen et al. In 2009, whereby they suggested less than 10 meters per million years based on studies of using the kimberlites. Studies of onshore sediment accumulation, particularly on the west, in the Orange and the Walvis Basin, they also found similar results that are consistent with low denudation rates in Southern Africa since the Cretaceous period. So these models, and there is a complete list of studies that have presented data that is different from, well, the generally accepted model of Patrician Mott. In a review that I recently did, you can find it on that reference. However, all these studies, they're consistent with the warming up of, or rather drying up of Southern Africa, whereby particularly in the last 5 million years, the climate has become more arid. Okay, now let's move our attention to what we have learned from cosmogenic nuclides. Well, in Southern Africa, particularly in Namibia, South Africa, Lesotho, as well as Eswatini, there is about 25 publications that have used cosmogenic nuclides in different parts of the landscape, that is on the escarpment itself, in the interior plateau, as well as on the coastal plain, all the way from the east in the Kruger National Area, around the South African coastal plain, all the way to Namibia. And on average, all these studies, all 25 of them, they yield an average denudation rate of less than 5 meters per million years for both the interior plateau as well as the coastal area below the escarpment. And on the escarpment itself, the denudation rates, they are very variable, but on average, they are less than 20 meters per million years. And this is since the Pliocene. Okay, so I thought I could use some 3 examples of papers that have worked on this topic. And the 3rd study ever conducted in Southern Africa was actually that of BML Caf in 2001. And in this study, it was a very comprehensive study where they used 66 samples of bedrock sediments as well as clasts, and they were using both beryllium-10 and aluminum-26. It was actually a very good study. I actually don't know how long it took them to do this study, given that the processing behind this, as you may have realized earlier in the talk, it is very tedious. And with that, they produced a very good data set. And from that data set, we can see that looking at a transect of Namibia, of different parts in Namibia, from the coast across the escarpment into the highlands of the interior plateau, in different sections of the West, there is no spatial pattern or trends that stand out for these areas. Despite that, the mean annual precipitation of the areas, for example, in the coast is less than 25 millimeters per year, whereas in the highlands, it is greater than 400 millimeters per year. And another interesting thing is that out of the 47 samples they used, about 36 samples, or 37 samples of the bedrock, they yield erosion rates that are less than 5 meters per million years. However, what was interesting is that the bedrock erosion rates are lower than the basin-wide erosion rates, which are about 16 meters per million years in the escarpment zone, and then they are slightly lower at 12 meters per million years in the highlands, and about 8 meters per million years in the coastal areas. However, the large river systems, they yield basin average erosion rates of 3 to 9 meters per million years for the entire West. Right, and the ventilated clasts in the Namib Desert. So these are clasts that have been polished by wind erosion in the desert. They found that they yield surface residence times up to 1.8 million years in this area. And I'll come back to what all this means as I give the concluding results. But let's move to another study, which was that of Erlanger et al. In 2012. And this study was looking at the rock uplift rates in South Africa, and they were doing it differently by using the isochron burial dating of fluvial and marine terraces. So they used struct terraces of the Sundays River near Port Elizabeth, as well as the uplifted marine terrace near Devon. And by using simple burial dating as well as isochron burial dating, they determined that over the past 4 million years, based on the burial ages they determined for the struct terraces of the Sundays River, the long-term incision rate of the Sundays River was about 16.1 plus minus 1.3 meters per million years, a value that is significantly lower than the suggested 100 to 200 meters per million years by Patrician mode, but consistent, of course, with other studies of thermochronology and cosmogenic nuclides. And for the marine terrace near Devon, they determined an uplift rate of 9.4 plus minus 2.2 meters per million years. And overall, this work showed that there is no evidence of rapid post-Pliocene uplift in Southern Africa, particularly on the eastern edge, where about 1,150 meters per million years of uplift has been suggested. In the interior plateau, in the cradle of mankind, several of us have worked there. Majority of the studies in this area, they focus on the burial dating. However, there's a few studies that have done denudation rate studies, and all these studies, they show that on average, the denudation rates are less than 5 meters per million years. However, we can see, based on the bedrock, as you can see that they go as far as over 16 meters per million years. There is some local dynamic processes that are related to mass wasting and scarp retreat. But this is easy to understand because the area of the cradle of mankind is the Dolomites of the Malmani subgroup, and that is characterized by cave deroofing as well as other dynamic karst processes. Soils in the cradle of mankind, I showed in my PhD work that they yield surface residence times up to 1.5 million years. And it is interesting when we compare with 1.8 million years west of the escarpment in Namibia, and together with 1.2 million years for the area east of the escarpment in the Kruger National Park. whereby this area is the wet, the most wet area in Southern Africa, and that is the most dry area in Southern Africa. And of course, we know in the Johannesburg area, we are sort of somewhere in between that in terms of climate. Okay, so I want to conclude here. I thought I could use a simple, some few examples, but in my paper where I did a review of all the cosmogenic denudation data of Southern Africa, you can go and look for more studies there and look in detail at the data. However, cosmogenic nuclides, well, they offer a diverse and useful isotopic method that helps us determine rates and ages of surface changes and processes. And these help us with a better understanding of the evolution of Southern Africa since the Pliocene. And all the studies that have used cosmogenic nuclides in Southern Africa, they show that while the landscape is locally dynamic, as a whole, it is on a steady state and eroding slowly, with little changes in the 10 to the 5, 10 to the 6 year time scales. And these results, they offer a high resolution window in that time scale, and the results are consistent with thermochronology results that are in the 10 to the 7 year time scale. And I would like to conclude with this slide.
Great, thank you so much, Tebogo. That was a really interesting talk you got there. Really interesting stuff going on. If anyone would like to ask questions or make comments, you can raise your hand. Use the little raise your hand function, and I'm sure Tebs will be happy to answer for you. Silence from the audience.
Yes, this is actually very common with the topic of cosmogenic nuclides, particularly here in Southern Africa.
We had a hand that popped up. Celia's. Was that a yes or a no? Okay, it's gone now, but we've got a question from Stuart. You can unmute yourself and ask.
Hi, Tebogo. Great talk. It's a subject that's of great interest to me. I would like to ask you, do you think that this method could be used for dating stone artifacts?
Yes, hi, Stuart. Yes, indeed. In fact, I neglected including that aspect of this work in this presentation because I wanted to focus exclusively on the denudation rate data. However, there is a few studies that have used burial dating of, well, in archaeological sites. Majority of them are in the Cryophyllene kind in the caves, but there's a few studies in Northern Cape, for example, those done by Ari Matmon and his colleagues in Wonderwork. But yes, the technique is very useful for that, for determining ages of stone artifacts or any surface processes or surface deposits that were formed since the Pliocene.
Thank you. So similarly for exposure dating of stone artifacts.
Yes. Yes. So if it is artifacts that have been exposed for quite some time, then exposure dating would work very well. But in most cases, people prefer to use burial dating. It depends on what, well, that specific area is based on, if it is an old exposed deposit or an old buried deposit.
Thank you very much. Perhaps we can chat about this further at some stage when we can meet one day.
Yes, certainly. I'd be happy to do that because I think we're at the forefront of setting up a capacity for these methodologies in the country, in South Africa.
One day.
Good stuff. Thank you.
Okay.
Okay, it looks like we have Celia's back. He made it back in. Let's see if your microphone's working and you can ask your question.
Good afternoon. Can you hear me?
Yes,
Yes.
we can.
Excellent. Okay, thank you very much for that talk. I have to admit I know very little about this subject, and that's why I was interested to sit in on this talk. So please pardon me if these questions sound stupid, but I just want to know the gist of it is you measure the amount of time a rock has spent in the sunlight. Is that correct?
Yes, well, not necessarily sunlight, but yes, exposed on surface to cosmic rays.
Okay, so if a rock was lying in a cave and it wasn't exposed to sunlight at all, would you still be able to do this dating on the rock?
Right. So if a rock that is in a cave was never on surface, no, we cannot. But if it is in the cave, okay, it may have been broken from the walls of the cave, then we cannot. But if it was ever on surface and then washed into the cave, then we are able to do burial dating on that piece of rock and determine its burial age.
Okay, wow, that's really cool. Thank you, Doctor.
All
Pleasure.
right. Do we have any further questions from the floor?
One question for me,
One in the
Natalie.
chat. There's a question in the chat. It reads as follows. Do changes in
just got it.
sun's activity or reduced incidence, example, terms of higher volcanic activity reflect in the amount of nuclides generated, or is the time scale too small to represent? Okay, so this is a very good question from the perspective of cosmogenic nuclide production. So yes, changes in the, well, in anything that affects our atmosphere are important. So for example, high volcanic activity will make our atmosphere very cloudy, and that will make the atmosphere dense, and that can modulate the incoming cosmic rays and the production of cosmic rays. So these do affect the cosmogenic nuclides that are ultimately formed on the atmosphere, which are meteoric, and those that are formed on the surface, which are in situ. However, there are different scaling models that scale, for example, the Earth's magnetic field over time, as well as scaling the altitude and the atmospheric depth over time, in addition to the latitude over time, because when you are at the poles, there is high production of the cosmogenic nuclides compared to when you are on at the equator. So I hope that answers your question fully. I have incorporated other aspects such as the geomagnetic field as well as altitude, in addition to the sun's activity or anything that can affect our atmosphere and the incoming cosmic rays. Okay, I'm not sure if there's any other question.
Tebogo, one from me. How do these techniques compare to optical luminescence dating?
Right. So cosmogenic techniques are superior to luminescence dating. Optically stimulated dating, in terms of dating burial, it has a lot more challenges than cosmogenic burial, and it is limited in terms of the age range. Typically 150,000 years is the maximum limit that many people place on it, with reasonable accuracy and precision. However, for example, in the cradle of humankind, I mean, ages as old as 350,000 have been determined. But using cosmogenic nuclides, we can go all the way back to about 4 to 5 million years with very good precision and accuracy. So cosmogenic nuclides are far superior than luminescence dating, also because it is not just one form of dating, but different forms of dating. Also, how you combine cosmogenic nuclides. For example, you can use a single nuclide, let's say just beryllium-10 on its own, and use it for a particular process. But when you combine beryllium-10 with helium-3 or neon-21 or aluminium-26, you open up a lot of other interpretations of the data that results from that. And you can do from dating to determining rates. And as a result, they're just superior.
Thank you for that.
Okay.
Natalie, any more questions that you see?
I see one in the chat. It reads as follows: regarding the established rates involved in this form of dating, are they also accurate for extraterrestrial rocks, meteorites? Yes. In fact, in the early development of cosmogenic nuclides, which in fact I neglected to mention earlier, that this technique, it's young compared to other dating techniques in geology. At most, it's about 3 decades long or old. And earlier work was mostly focused on dating or understanding extraterrestrial materials such as meteorites, because the production of cosmogenic nuclides in extraterrestrial materials was better understood than on Earth. It's only recently, well, in the last 2 decades, that we are starting to understand better and better what controls the production of the nuclides in Earth surface materials. So in extraterrestrial materials, that's where initially the focus was on for this method. I'm not sure if this is another question. Yes, there's another question, reads as follows. The kind of rate measured through rock dating, or are there any other techniques that can be used in formulating rate of sedimentation? Okay, I actually said reading the question halfway, so you mentioned sedimentation rate somewhere in your talk. If memory, okay, right. My question is that kind of rate measured through dating or right. Okay, so I think this question speaks to what exactly happens with determining sedimentation rates. So sedimentation rate is mostly a matter of how you sample. You might have a soil profile, or maybe a structure race profile that you have, and depending on how you sample the profile, for example, you can do a depth profile sampling from the surface to depth of that profile, and by looking at the differences of the concentrations at different depths, you can then make a regression of what the sedimentation rate. And this is similarly to how incision rates are also determined. So many of the different methods of cosmogenic nuclides, for example, determining slip fault rates, determining soil production rates, these are dependent on how you sample. So it's always a matter of intelligent sampling based on a hypothesis that you hope will answer your question. And depending on what results in terms of the concentrations of the cosmogenic nuclides, depending on the fit of those results with the hypothesis, then you can determine the different techniques that help you answer different forms of rates, incision, sedimentation, etc. I hope that answers that question fully. At this stage, I don't see any more questions.
Yeah, are there, well, we've got one from Sasha. unmute yourself. Okay.
Hello there. How are you?
Hi, Sasha.
Might not be the best question, but just wondering in terms of depth of penetration into your surface, you say it's basically on the surface, or you basically measures surface dating, but how far can it penetrate into the ground? In terms of meters, yes.
Yes, that's actually a very good question. It was somewhere in my slide, but I actually didn't speak to this. So in terms of production of cosmogenic nuclides, there are several mechanisms. The most common is spallation, which I spoke a bit about for beryllium-10 and aluminum-26 in quartz. And spallation is responsible for 95 to 98% of the nuclides in situ on the surface. However, with depth up to 3 meters, spallation drastically reduces to 0%. And then meteoric production. So this is production by negative muon capture reactions. So this is more physics. This then dominates at depth of about 3 meters up to great depth, but I think the safest depth is up to, say, 10 meters with very good accuracy and precision. But depending on what you want to do, if you are doing exposure dating, people often don't look at the meteoric production because it is at surface. But when doing burial dating, the meteoric production becomes very important, especially if it is at great depth, say 15 meters depth or 10 meters depth. Then the meteoric production becomes very important because there we are dealing with a lot more production. So I hope that fully answers your question. But yes, there are several mechanisms of cosmogenic nuclide production. It's just that we tend to focus on spallation production, given that it produces up to 95, 98% on the surface.
Thank you.
Are there any more questions or comments? I see we have Natalie back with us. We lost her for a few minutes.
Yes, sorry, I think I'm back. The internet today is just not happy.
I think probably if there are no more questions or comments, we can close the meeting. Natalie, do you want to close for us?
We can do so. Again, thank you so much to Terry for sponsoring this month. And thank you very much to Tebogo for joining us today. That was really interesting. So thank you so much.
Well, thank you for everyone who came to listen to the talk.
All right. Everyone have a great day.
Thanks, everyone. I'll close the meeting now.
Right.